Look at all this hardware. This is 5 computers with a total of 30 CPU cores and 160 GB of RAM. Using the build I will show you in this video, it is possible to put any number of computers in your Homelab, from 1 to unlimited, without wasting space or money. Now, I have built computers for over 30 years, and for this build I have done extensive experimenting and testing to find what I think is the best way to put computers in my Homelab. I want to have as much hardware as possible to have room to experiment with a lot of different things. But my Homelab is small, and so is my budget. So I had to find a way to maximize performance for a low cost and minimize the size of the build. And in this video I will show you exactly, step by step, how I did it, so you can do the same build. Before we start the build, let's have a quick look at the components. The motherboard is the ASRock B450M Pro 4R 2.0 Micro ATX. One interesting feature on this motherboard is that it has a USB 3.1 connector. I'm thinking that could become useful later when I want to upgrade the network connection to, say, 2.5 gigabits using an USB dongle. The CPU will be this AMD Ryzen 5 5600G with a base clock of 3.9 GHz and 6 cores. This CPU comes with a fan that works well for this build. We want the CPU to have integrated graphics, as adding an extra card would take up more space. And we're building servers here, not gaming computers. Then for RAM, we will use two 16GB sticks for a total of 32 GB. This is 3200 MHz DDR4 RAM from Corsair. Ideally, we want to use ECC memory, but since that is more expensive and complicated, we will stick with regular RAM. It's not like the Homelab will run production workloads anyway. Finally, for storage, we will use this Samsung 990 EVO 1TB M2 card. When having this many machines, we can actually experiment with hyper-converged storage, which may be a topic for another video. Now let's talk about the trade-offs that went into selecting these components. Even if these components soon will be obsolete, I think the trade-offs for this type of build will stay the same. So, what are the trade-offs? Well, we want the computers to take up as little space as possible, and we want them to be as cheap as possible. However, we still want okay performance so that we can actually use them for real workloads. And we also need to think about power consumption. Taking all of that into account, what would you have selected? Let me know in the comments. You may have noticed that we are still missing two pieces for a regular PC build: the case and the power supply. And this is where this build gets interesting. For power, we could use regular ATX power supplies, but they take up a lot of space. We could try to connect several computers to the same power supply, but then they would not be independent. I researched a lot on the power solution and finally found a way to solve it. So we are not going to use regular ATX power supplies. Instead, we will be using these 12-volt power bricks, which I bought on AliExpress for about $20 US. They are put 12 volt at a max of 12.5 amps, so they are 150 watts. So this is a bit unusual, right? You might be asking, will this be enough power? And how do we even connect this to the motherboard? First, let's explain how we will connect it. We have 12 volt coming out here from the power supply. However, the motherboard needs an ATX power connector, which has several voltages, like 3.3 volt, 5 volt, and even minus 12 volt. So directly connecting the power brick will of course not work. To solve this problem, I found these 12 volt to ATX converters, also on AliExpress for about $20 US. The way this works is that the converter takes 12 volt input, like this, and then provides a ready-to-use ATX connector with all the correct voltages, and even some extra SATA power connectors if you use that. I'm not sure why these converters exist, but my guess is they are used for cars, where they convert 12 volt from the car battery. Anyway, they fit perfect for my use case here. Now for the second question, will this setup give enough power? In the beginning, I was actually a bit skeptical that this would work. We can try to calculate the theoretical power consumption of our build. The CPU is the most power-hungry component, and it has a thermal design power, or TDP, of 65 watts. However, when researching, I discovered that the TDP does not directly translate to real-world use. There is also added power consumption of the other parts, for which it is hard to get good numbers. So, instead of calculating, I measured real-world consumption under high CPU load to see if it was enough. And yes, the measurements, as we will see later, tell us that the power is enough. I also did this exact build a few years back at another location, and it has been running for a long time without problems. So yes, I know for certain this power setup will work. Now let's move on to the mounting solution. We could use a regular PC case, however they take up a lot of space, so we are not going to use a regular PC case. Instead, we will be using this simple piece of plexiglass. This is a 30 cm square with a 4 mm thickness. It will act like a blade to mount everything on. So we will put the motherboard and the power converter on this. And we will also add a switch for power and reset. I got this switch with LEDs from AliExpress. It costs about $1. In addition to the power switch, you can also get this type of buzzer on AliExpress for about $1. It is not necessary, but hearing that satisfying beep that says the computer is working is really nice. To mount the motherboard, you will need regular hex head motherboard stand-ups like these. They come in some variations, and any variation is fine as long as they have coarse threads that can bite into the plexiglass. The same standoffs will be used to mount the power converter board. You will need 8 standoffs for the motherboard and 2 for the power board, so 10 standoffs in total per blade. You will also need 10 screws. During more than 30 years of PC builds, I have accumulated quite a lot of spare standoffs and screws. I think they are actually the same today as they were 30 years ago. But if you don't have any on hand, they are easy to source from Amazon or AliExpress. To mount the cables that came with the power board, we will use zip ties through holes in the plexiglass. The holes will be 3 mm, so the zip ties need to be smaller to fit. The ones I use are 2.5 mm wide. We will also mount the power switch with this. You need 6 of these zip ties in total to mount the power cables and the power switch. You also need some more zip ties to bundle up unused power cables. If you want a nicer mounting for the power switch and power connector, I designed these holders that you can 3D print. You will need 4 M3 8mm screws to fasten them. I will link the files in the description. However, they are not necessary. Only using zip ties will work just fine, so you really don't need to 3D print anything for this build. To mount the blades, we will use these aluminum rails. These rails are actually meant for attaching tents to caravans or RVs. To find them, you want to search for Keder rail or awning rail. It has a groove of 4 mm where a rope from the tent is supposed to go. However, this also fits our 4 mm plexiglass perfectly. You will want to get one that has the track facing upwards, so the plexiglass blade can slide in. Since they are widely used for tents, they are quite easy to find and quite cheap. I paid about $11 for 1 meter of rail. You can mount these rails wherever you want the blades to go. In my case, that is in a 19-inch server rack. So for this I will use 2 regular rack shelves. One shelf mounted in the bottom and one reversed shelf on the top. I prefer shelves that already have holes in them where I want to mount the rails. This way I don't have to drill. However, usually near the edge there are no holes, so there we need to drill. In addition to the shelves where the rails are mounted, I also use a smaller shelf. I mount this on the back of the rack and it is used to hold the power bricks. I simply zip tie the power bricks to this shelf. And now we have gone through all the components needed. So let's start building. And the first step is to remove the protective plastic from the plexiglass. With the plastic removed, it's now time to think about the holes that we're going to make in the plexiglass. And to help with that, I designed these 3D printed hole templates. As you can see, these are in 3 parts. So one part is here, one part is here, and one more part here. The reason they are in 3 parts is because my 3D printer cannot print the full size of the whole plexiglass. Now you don't need to use these templates. As I said before, you don't need to 3D print anything for this build. You can just use a regular ruler instead to measure where the holes should be. There are 4 sets of holes here. One set is for the power cable, another set is for the power converter, the third set is for the power switch, and the final set is for the motherboard. I made a drawing of all the holes that will be linked in the description. Let's start with the holes for the power cable, which will go here, and then it will be zip tied through these holes here, here, and here. Let's start with the method where we don't use the templates. For this we will use the ruler and also a pen. I found that this carpenter pen with the yellow color works really well and is easy to get off the plexiglass. As we saw in the drawing, these holes are located 18 millimeters and 36 millimeters from the edge. So let's make marks at those locations. One more time, further down, and then draw lines across the marks. Now make marks from the top edge at 7.5 millimeters, 120 millimeters and 220 millimeters. Then make lines at these locations that cross the previous lines. Now we can use an awl to make notches where the holes should be. Let's use the template to make the notches. I fastened the template to the plexiglass using tape so it will not move when I make the notches. As we can see, the holes in the template line up quite well with the lines that we drew, so using either method is fine. The accuracy of these holes doesn't matter that much, since they are only used for zip ties. They can be 1 to 2 millimeters off and it will still work fine. Now that we have made the notches, we have a good starting point for later when we are going to drill the holes. Now I will go ahead and make the notches for the power converter board and the power switch cabling. These holes doesn't need to be that accurate either. 1 to 2 millimeters off is fine. If you're not using the templates, you can find all the measurements for these holes in the drawing, which is linked in the description. With the notches in place, we can go ahead and wipe off the lines. The final set of holes is for the motherboard, and here accuracy is more important. So if you're not using the templates, I suggest that you make a reference line and then measure from the actual motherboard itself. So let's use this point as the reference point. It is located 30 millimeters from the left edge and 165.1 millimeters from the top edge. So first, let's make a line 30 millimeters in from the left edge. And then another line 165.1 millimeters from the top edge. With the reference lines drawn, we can use the motherboard itself to pinpoint the locations for its screws. It helps if we have already mounted the CPU and the fan, because that means you can put the motherboard upside down like this. First, we will mount all the standoffs on the motherboard itself, because that will help us to pinpoint the location of the holes that we need for the screws. Now with all the standoffs mounted, we can put the motherboard into the correct position, and then we'll just turn over the whole thing, including the plexiglass, like this. And then we try to line up the reference point here with the standoff. Once you have that lined up, you can go ahead and mark all of the other standoffs. You should now have made 8 marks in total. The important thing here is not exactly where the marks are on the plexiglass, but rather the internal distance between all the marks, because if it's not accurate, you will not be able to fit the motherboard. Now let's turn this back over and remove the motherboard. And then we can put the template back on and see if the holes match. Okay, so let's see how they align with the template. So as you can see here, they're a bit off, but they seem to be off by the same distance. So that should actually be just fine. Now I will go ahead and make the notches for the motherboard using the template. There are of course other ways you can transfer this set of holes from the motherboard. Maybe you can print a piece of paper with the correct scale and just tape it to the plexiglass and make the notches that way. Or you can draw it on a piece of paper as accurate as you can and then again tape it to the plexiglass and make the holes that way. Do you have another idea how to transfer the holes from the motherboard to the plexiglass? Please let me know in the comments. Now with all the notches done, it's time to drill the holes. And the holes are in general all 3 mm in diameter. However, depending on how you want to do things, there are some exceptions. So if you want to use these holders that you can 3D print, this is for the power connector and this is for the power switch, then these holes should be 2.5 mm. So these two, 2.5, and these two, 2.5. If you're using the zip ties, they should also be 3 mm as every other hole. And the final exception is this hole here. If you want to use a wider zip tie to bundle up all the excess power cables, you can make this hole 4 mm. So with all that covered, let's remove the template and start drilling. And now that our plexiglass has more holes than a Swiss cheese, we can finally start mounting things on it. Let's start by mounting the standoffs. So to do this, I have a screwdriver because you need a bit of force to get them into the plexiglass. And I'm using the coarse thread standoffs because they fit well in the 3mm holes. Maybe you can use fine threads if you use 2.5mm holes. I haven't tried that, but these works well. And I'm gonna do all the standoffs for the motherboard and the power converter board here. The reason I do the standoffs first is because then I know what holes are taken by the standoffs and the holes left are the ones for the cabling. So the next step now is to mount the cabling, and we will start with the power cable, and it will go here. To fasten it, we will use these 2.5mm wide zip ties, and to get a good grip we want to adjust this screw here. So the zip tie just comes between the screw and the edge of the plug here, and then screw it in like that, and then we have the perfect fit there. So once you have that adjusted, you want to zip tie the first part here, and I usually go for having the zip tie in this orientation, because then when you fasten it you will get the pointy end inwards, so you don't hurt yourself on that later. In there you go. You have it nice and snug there. Then we will do it one more time further down here for the rest of the cable. Finally, one more time for the last part. So now that we have it fastened all the way like this, we can use pliers to just make sure that it is super snug here. And once we've done that, we can use the cutter to just cut off the excess of the zip ties. With all that done, we can now check that we have a good connection here with the power brick. So if not, you can just twist this a bit until it comes into a good position. If you printed the holder for the power cable, you will do this slightly differently. And I will show you on this different piece of plexiglass where I drilled 2.5mm holes here. So let's switch to this one. And in this case, you want to fully remove this screw here and put the power cable through. It comes out the other side, and then screw it back here like that, and then you put it in the same position, but this time we will screw it into place with two M3x8mm screws. Once you have that screwed in there, you got a nice fit for it, and then you just zip tie the other two parts like before. And this gives you a little bit better connection here, because when you pull back here, this holder will really hold it into place. Now with the power brick cable done, let's move on to the power switch cabling. So this is quite long, I think it's about 50 centimeters. We could of course cut it off here and just solder it back on, but that's a lot of work, so I usually just keep it like this and then just have the excess part of it under the motherboard like this. The first thing we want to do is to zip tie the switches themselves onto the plexiglass, and to do that we want to orientate them like this, so we get the plexiglass here. So it's easiest if you just first put the zip tie through and just put it in position and close it just a little bit like that. Now we have a nice starting point for mounting the power and reset switch here. So let's put them into place. Let's tighten it up. So once they are in there, you will see that they will move back and forward like this. To fix this, we will just put another zip tie right here. So once we get all of this cabling zipped down here, the switches moving will not be a problem anymore. So now that we got the first part zip tied down here, we want to flatten the cable, and just at the edge of the plexiglass we want to fold it so it doubles back up again. And that will take care of all the excess cabling, and we will be left with this part here then to connect to the motherboard. So let's zip tie down this part of the cable as well. One zip tie goes here, and then one last zip tie over here. And with that done, we just tighten a little bit with pliers and then cut off the excess with the cutter. If you printed the holder for the power switch and reset switch, you will do this a little bit differently. So here I have the other piece of plexiglass where I made the 2.5mm holes over here for this holder. So first we want to find the correct orientation of the holder. So this has a back side where you have narrower holes that are not symmetrical, and you have the front side where the holes are larger and symmetrical. This is where the switches will poke out, and we will start by inserting the LEDs. So we want the power LED, which is the green one, to go here, and then we want the hard drive LED to go here. So once you have the LEDs in there, it's time to put the switches in. And I prefer to put the power switch under the power LED, just to remember which one is the power switch. You can check here in the other end, the yellow one is the power switch. So let's put the power switch over the green power LED, like that. And then we put the purple one on top of the hard drive LED. It's a bit of a tight fit, but it should go in there. And once they're in there like that, then it's correctly mounted. And you can also check the LEDs here, that they are poking out the correct amount here. Maybe it's just me, but to me this looks a little bit like Darth Vader. Look, I am your power switch. I probably should have printed this in black for better effect. Well, anyway, let's get this mounted onto the plexiglass. And to fasten it, we will use the same M3x8 screws that we used for the power cable holder. You can actually screw one in here first, a little bit, and then you can put it like that. And then take the next screw. And once that is tightened, you can go back to the first screw and tighten it fully. And then you just fold the cable and zip tie it just like we did before. And now that we have all the cables mounted, we can go ahead and mount the motherboard. Now you want the back side of the motherboard with all the connectors to go to the same end as the power connector here. And this is the moment of truth to see if we manage to get enough accuracy in the holes for the motherboard. So we'll try and line it up here. And it seems like it lined up quite well. So let's go ahead and screw it in. And when you put in the screws for the motherboard, it's a good idea to not put them fully in, because that will give you a bit of wiggle room later if you need to adjust a little bit. So just put them in with a few turns at first, and then go over all the screws one more time to tighten them. And now that we have the motherboard mounted, we can go ahead and mount the CPU, and we'll just make sure that the edge that is marked here is mounted here, so it should go in smoothly like that. And then we just need to remove these plastic thingies here in order to mount the fan, because this fan is mounted with screws. And during the years of PC builds, I've seen all kind of brackety, thingity, plasticky things to mount CPU fans. And finally someone figured out you can just use screws. It's quite amazing. I like this. So let's remove these plastic adapters. We don't need them. There is a metal plate on the back side that will become loose when we do this, so we need to take care that it doesn't move. So now with the plastic thing is gone, we can mount the CPU fan. And I found that if you put it like this, it's better, because if you put it like this protrusion here will go against the RAM here. So I will just put it like this. You want to screw them in a little bit at the opposite sides until they're all the way in. So now with the CPU fan mounted, we just need to attach the cable to the motherboard. And it should go here. So let's put it there. And then we want to get rid of this excess cable, so let's tuck it under here with some of it on this side and some of it on this side, like that. And now let's go ahead and mount the RAM. And I know from reading the motherboard manual that they should go in this slot and this slot. And with the RAM mounted, it's now time to mount the M2 drive, and it goes here. and we need to screw it down using the super tiny screw that for some reason comes with the motherboard instead of coming with the drive. And now let's connect the motherboard headers, and they should go over here. The process of attaching these cables is just as fiddly as it has been during the last 30 years. I wonder if this will ever improve, and probably I got one wrong also, as usual. Anyway, with all that mounted, there's just one final piece missing, and that is the power board. And it goes here on the standoffs. And before we screw it in here, we want to make sure that we include this grounding cable here. So we just put it on top and then put the screw in. Now with the power board mounted, we just need to attach this cable here. And then we need the ATX cable. And the ATX cable has two ends. One is longer than the other. The long one should go into the motherboard, and the other one should go into the power board. And we also have this one extra that we want to connect to the CPU power. I want to push it all the way down until it clicks with the locking mechanism. And same for the one that goes to the board. And all these extra cables we don't need. This is for old hard drive, and this I think even is for a floppy drive. Been a long time since I saw one of those, and this is for SATA. But this one we need, it's extra power for the CPU over here. And it can only go in one way, so it should be there. You actually get one extra connector for power here, and you also get an extra cable that you can use for that connection. But I noticed for this motherboard and CPU, we don't actually need this cable. Now to tidy up these cables here, we will just put a zip tie through this hole here. And I made this hole 4 millimeters so that I can use this larger and longer zip tie for this. Let's move this over so we don't get the pointy side towards us. And now that this is nice and bundled up here, we just need to zip down this cable also. And I will attach it to this other cable here using a small zip tie. And now we are almost ready to power this computer up. One final thing we need to add is a buzzer. And it should go here. And let's zip tie it to the other header cables here. And with that, all the components are now mounted and we are ready to power up the computer. Okay, I have connected a lot of stuff here in order to power up the computer. So I have this portable monitor here, which is connected to power, to this power brick here, and HDMI here to the computer here with HDMI. And we also have a USB connection to a keyboard here. And in addition, we have power here coming from the power brick. So let's go ahead and try and power up. So to do this, we will press the power button over here. So it's the one next to the power LED here. Let's see what happens. Moment of truth. Power LED is on and the CPU fan is spinning. And we have picture. Okay, no beep, but picture, and it says new CPU installed. Press Y to reset FTPM. Okay, so let's press Y. And this makes it reboot, it seems. Let's see what happens. So the CPU fan is now spinning up. And let's see if we can get it to boot. Picture. And beep. Yes, it's alive. No boot device. Yeah, that's perfect. That's expected. Okay, so before we install anything, let's just do some adjustments in the BIOS. So we will reset. And for this, we can try the reset button, see if it works. Should be this one. Yeah, that worked. And then we just need to be fast with pressing delete on the keyboard. And that takes us to the BIOS. So there's basically two things I want to modify here. One is the amount of memory that the integrated graphic takes up. I don't really want to use the integrated graphics for anything but the console. So I want to minimize the memory it takes because the memory is shared between the CPU and the GPU here. And we're not going to run AI or anything on this kind of graphics. So let's minimize the graphic memory. To set the graphics memory, we need to go to Advanced and then AMD CBS and NBIO and then GFX configuration. And then we set the iGPU configuration to specified, and the frame buffer will set to 64 megabytes. And that's it for this setting. The other setting I want to do is make sure that the computer powers on if there is a power loss. So it's in the onboard devices configuration. Restore on AC power loss. We want to change power off to power on. When the power comes back, it will automatically power on again. Okay, let's save that and exit. Now we're going to test the power supply. So in order to do this, I installed Windows and OCCT, overclock checking tool. This tool has a bunch of tests it can do, like CPU plus RAM and so on. It also has a power test, which tries to maximize the power draw. And we will get to this test later, but I will start with the more simple test, just CPU plus RAM. I also installed a power meter here on the AC plug for the power brick. So this cable that's here goes to the power brick over here. And then the power brick goes to the computer. So here you can see, currently it's drawing 33 watts and 32 watts. And this will change when we engage the test. And we need to remember that this is the primary side of the power supply. So the power supply is 12 volts, 12.5 amperes, which is 150 watts. But that 150 watts is on the secondary side that it delivers to the computer. So the primary side might draw more here because some of the power is lost inside the conversion. Before we start the test, let's take a baseline measurement of the temperature of the power brick. So the maximum temperature of the power brick now is 36 degrees Celsius. You can also measure the CPU and the chipset here, but they have internal sensors, so it's more interesting to look at the power brick here. So 36 degrees Celsius before we start the test. And now let's go ahead and start it and see what happens with the temperature. So now the test is started. And we can see here we have a power draw of 39 from the CPU and 32 from the graphics. And from the AC plug it's drawing now 87 watts. And the temperature is about 36 degrees Celsius on the power brick. This test will run for 1 hour and I will come back in 15 minutes and check the temperature and the power draw. We are now more than 15 minutes into the test, almost 16 minutes, and the temperature of the power brick is a maximum of 47.8. So it has risen a bit and the power draw is 87 watts. I will continue to run the test and I'll let it run almost to a conclusion and check the final temperature, and then we will go ahead and run the max power test instead. We are now 53 minutes into the test, so about 7 minutes left to go. And the temperature of the power brick is about 59 degrees Celsius. Temperature of CPU 74, of the graphics 70, and the power draw is about 90 watts. Okay, so the test is about to conclude in 5 seconds. And the temperature of the power brick is...
schedule is complete.
Okay, 59.6 on the power brick. And the test completed without any errors, no errors detected. So that is very nice. And I think this is what you can expect from normal use, or this is even an extreme case. If you're running web services and stuff like that, they will not use 100% CPU all of the time. So we saw it maxed out, now it's back to 35, but it maxed out about 90 watts. So we got a lot of room there up to 150 watts that it will deliver on the secondary side. Okay, so now I have let everything cool down and started it up again in order to prepare for the max power test. So the temperature of the power brick is now maxed out at 38.5 degrees Celsius. And let's go ahead and start the max power test. So we'll go here, max power, instruction set auto, and hit start here. And now the max power test is started. We can see that the power draw is about 147, 45 right now. and the temperature of the power brick is about 38.5, and we can see the draw from the CPU is about 77 watts, but now the graphics is also drawing more, 48 watts, so the tool is trying to maximize the power draw here, and the power draw is 150 watt even from the plug here. And I will let this run for 15 minutes or so, and we will come back and check the temperature. Okay, so we are 15 minutes into the test, and the temperature of the power brick is about 59 degrees at the max, 60 degrees, kind of like the test before. But what I noticed here is the cables are actually hotter than the power brick itself. So the cables are about 75, 76 degrees, and this cable also that goes back to the power converter board is also very hot, and it's about 70 degrees, and then we can go all the way back to the converter board here, and the converter board itself is not so hot, but the cables are probably not really dimensioned for running this much amperes as they are right now, but it's okay, they are still managing it. The test is now nearing the completion. There is about 1 more minute to go, and the power brick is quite hot now. It's at about 83 degrees Celsius. The cables are still at about 74, 75 degrees Celsius, and the power draw is stable at 145, about 145 watts. And now the test is about to complete here.
The test schedule is complete.
So we completed the full test, no errors detected. Power brick is at about 83 degrees Celsius, cables at about 74. I should probably also mention that I'm filming this in the summer, and the ambient temperature of this room is about 30 degrees Celsius. So during the max power test now, we saw that the power brick draw about 145, 148 from the power plug here. And that is close to the 150 watts that it will deliver on the secondary side. But to know really how close we are to the specified amount, we need to measure on the secondary side and see how close is the secondary side power usage to the 150 watts. And I will try to set up some way of measuring this. Okay, so I tried to set up a way to measure the power usage on the secondary side of the power brick. I've started the max power test, and I connected a voltmeter here. It goes to this connector here on the power converter. It measures the voltage coming from the power brick, and this clamp ampermeter is measuring the amperage coming from the power brick. To get the power usage, we just multiply these two values, because ampere multiplied by volt will give us the power in watt. Let's use the value of 11 volts and 10.6 amperes. This gives us a wattage of 117, and we have 141 on the input. So if we take 117 and divide by 142, we get about 82% efficiency of the power brick, which seems a bit low, but not totally unreasonable. And then at least we know that even if this goes up high, the secondary side is still more safe. So at max power test, we have a secondary side power usage of 117 watts approximately. And that gives us quite a bit of margin up to the 150 watts that it can deliver on the secondary side here. So I guess my conclusion from all this testing is that even if you have a room of 30 degrees Celsius ambient temperature and you maximize the power draw with an artificial test, the system is still stable. So for real world usage, this power setup should work well. Now we're going to build the housing for the plexiglass blades, and for this we're using this 19-inch shelf here, and we're using these aluminum rails, and the plexiglass blade will go into the track in the aluminum rail, and it will slide in like that. To fix the aluminum rail to the shelf, I'm using this M4 by 12 machine screw, and I'm also using this M4 nylock nut, and I'm also using this washer, which is 25 millimeters wide. And the reason I need it to be this wide is because it needs to cover this hole in the shelf, so it will go on the underside and it will prevent the nut from going through the hole, because the hole is larger than the nut. The aluminum rail is 1 meter long in total, so I need to cut it using a hacksaw. And I need to figure out where to cut it. And I will start by marking the middle of it, because then I can cut it into symmetrical pieces. Now I know from taking some measurements on the blade that I can fit 5 blades in here, so I need 5 of these aluminum rails. And if I take a measurement across here, the shelf is about 43.5 centimeters wide, and if I divide that by 5 I get 8.7 centimeters. So 8.7 will place me somewhere around here, which means I will use these holes here. So if I align the middle mark here with the back side, I see that this hole in the rail will come here, which is not good because then I can't go through. So I need to move a bit forward, which is not really a problem. And if I do that, I can actually fit the screw through here, which is good. But then I discovered another problem, which is this screw hole here will then come here, which doesn't work. So I need to move a little bit forward again to get this screw in also. The plexiglass is 30 centimeters, so if we align it with the front here, it will go until here somewhere. And then we will have the cut here, so we have this margin here, and this will work. The first aluminum rail will need to go here, and since there are no holes here, we need to drill holes. So we need to take a measurement from here to here and here to here to know where to put the holes here. So we will mark the position of the first hole. Then we put a mark here at the same position. And then we can move the rail into position so the hole is aligned with this mark. And we will make another mark here and another mark here. And now we know where to drill the holes. We also need to make another cut here in order to prevent the rail from poking out. And we want it to be a bit in, so it's not poking out at all. I guess it will be around here. Just let's take a measurement from the edge. So I would say that is about 12.5 centimeters in. So let's make a mark at 12.5 and make a cut there also. So now I cut the rail down the middle, and then I cut off 12.5 centimeters on each end. And I ended up with this, and this looks good. So we have a little bit of margin in here and a bit of margin here, and the blade will fit perfectly here. Now if we look at the other piece, you can see that it's actually not the same holes, so it will not work to put it like this, but this is actually what we want, because this is now a mirrored piece from this one, and this one will go on the top. So there will be another shelf, and the blade will go here, and the reversed shelf will be here. So this one will be used for the reversed shelf. So with all those measurements sorted out, what's left now is just to cut all of the rails and make all of the holes in the shelves. Okay, so all the cutting is now done, and I cut down 5 of the 1 meter rails, and I got 5 of these pieces and 5 of these pieces. So they are not the same, and these will go on this shelf that has the holes here, and these will go on the other shelf that has the holes here. So this will be the reversed shelf, so it will go like this, and then we have holes here and holes here. We will get a blade there. Now let's mount the rails to the shelf, starting with this shelf. For the ones that I drilled holes for, I can use the smaller washers here and then the nylock nut on top. Now with the first rail mounted, it's time to mount the second rail, and I did some measurements. It should be 8.7 centimeters approximately from here, and it needs to go here actually in order to make room for the first blade here. And for this I need to use the large washers. And we leave this a little bit loose like this first, so we can adjust it later. And now let's adjust this so it has the same distance as the other one. And we want it to go as far to this side as possible, because the distance here needs to be 8.7. And now we just repeat this for the 3 remaining rails. And then for the reverse shelf, we just do the same process. And now with all the rails mounted, we can mount the shelves in the rack. Okay, so here we are now at the rack where we'll be mounting the shelves. Hang on a minute, let me just see if I can turn this noise amplifier off. Yeah, okay, that's better. Okay, so as I was saying, we will mount the shelves here at the bottom. So the bottom one will go here, and then the reversed one will go on top of it. Okay, so now we got the bottom shelf mounted. So I need to measure here. How high should the reversed shelf be in relation to the plexiglass here? So we'll try to put the blade in here. So it goes up to this mark here at between 7 and 8. So let's try to put it there. By the way, I found this cage nut insertion tool that you can 3D print. So I 3D printed one, and it actually works. So I'll be using this to insert the cage nuts. Now let's check if the blade fits. It seems this is a bit tight here. There's just a millimeter or 2 missing here. So I can try and push this shelf up and push this shelf down and then fasten it again. Okay, so with all the screws loosened, this slides in nicely here. You can see here if I push this, it will pull down on the shelf. So I just leave it like this. And now we actually got a good fit here. So it's snug and it will not come out unless you pull it. But still it's smooth enough to get it in and out. And now I turn the rack around so we can mount this smaller shelf, which will hold the power bricks, and it will go somewhere in between the front shelves, maybe here. So let's get the power bricks mounted onto it. And for this we will use these zip ties to get the power bricks mounted. And since this is the back side, we want the power bricks to come out this way. Since the zip ties won't fit all the way around, we need to connect 2 of the zip ties together to make them longer. Now it's nice and snug in there. Now we'll just do the same for the rest of the power bricks. And now with all the power bricks mounted on the shelf, let's mount the shelf onto the rack. And now with the power bricks mounted, what we have to do is connect up all the blades, and then we can start the mount. So there you have it, all 5 computers installed with minimal space and money wasted. Making this video and documenting the build in detail took a lot more effort than I anticipated. So if you found it useful or interesting, I would appreciate if you leave it a like and consider subscribing. The next step now is to install software. I have not decided exactly what to install yet. Maybe it will be bare metal Kubernetes or maybe a Proxmox cluster. I will probably make a video about the software install, so be sure to subscribe to not miss that. So that's it for this video. Thank you for watching, and I will see you in the next one.